All right, welcome back, everyone. Today we've got a formal lecture. We'll have our usual Friday discussion next time. And this is one of our mathier lectures that we're going to have. So before we get into it, I really just want to emphasize and reiterate that this is not a math class, nor is this a stats class. So really, what I want you guys to take away from this lecture is the concepts. And because this is a leadership class, really what I want you to take away is the fact that you can interrogate these concepts. Why might these concepts not work for you when you are trying to make decisions in a data-driven world? So our topic today is Dags and Regression, which sounds really mathy. Let's get into it a little bit, right? So what we've done recently is introduce identification as the process of ruling out alternative explanations. And this is really important for coming up with causal effects. We want to rule out alternative explanations. So why did Annika spend all the way until evening at the driving range yesterday? Well, we can come up with a bunch of different reasons. She wants to hone her craft as a golfer. It was really nice out. She wanted to see her friends. If we can come up with some sort of way of ruling out alternative explanations, we can come up with a causal model. In our last lecture, we built on this concept of identification strategies of ruling out alternative explanations by introducing a very powerful one, experiments. In an experiment, you randomize groups between treatment and control. So it's a very compelling way of ruling out alternative explanations. Because what randomization does is reasonably convince most of us that groups in the treatment group are the same as people in the control group. Anything that you might observe, like height or weight, or things that you might not be able to observe, like innate ability, should even out between treatment and control. And that's why things like the polio vaccine trial was so convincing. Questions so far? So today we're going to continue this concept of our causal framework, and we're going to model this causal process using what's known as directed acyclic graphs. And this is a really verbose way of saying charts with arrows on it. Once we introduce DAGs, we're going to also learn about our next identification strategy, regression. And again, this is not a math class, this is not a stats class. We're going to learn about this from a very conceptual way, and we might also want to question those concepts. So when we're thinking about causal relationships, when we're thinking about causes and effects, and more specifically, when we're thinking about the effects of causes, what we want to do is design a credible identification strategy. What's a good way that we can rule out alternative explanations? And drawing out the way in which variables are related to one another can be immensely helpful. Specifically, we're going to draw out directed acyclic graphs. A DAG is a graphical representation of a chain of causal effects. It consists of nodes and arrows. The nodes are the variables, so yesterday's weather might be a variable. The outcome variable might be how much time you spent playing golf. And the arrows are the causal direction. So if you see an arrow between two variables, that represents a causal effect. Now, the causal effect might be based on some underlying unobserved process, some structural process, but that doesn't matter to us. We just want to know that there is an effect there. Because we are drawing arrows, it is directed. So when we think about these arrows, think about the causal effect moving forward in time. What makes it acyclic, which is just a word that means not a cycle, is we can never have a causal effect moving backwards in time, and we can never have reverse causality. So in that silly example from a second ago of Annika playing golf, the nice weather yesterday caused Annika to play golf yesterday. Playing golf in this silly example can never cause nice weather. Now this is a silly example, but we might see some more complex ones where maybe we want to push back against that assumption. So the funny thing about DAGs is, though you might not be familiar with the terms and the concept, you guys have already seen them before. In fact, we saw a really compelling one the other week of banana peel causing slipping. When we formalize this process into the DAGs that a social scientist might be more familiar with using, rather than using these silly pictograms, we're going to use letters to represent variables. So here I have banana, an arrow to S, banana causes slipping. Questions so far? Importantly, this structure places DAGs in our potential outcome framework that we learned a couple weeks ago to describe the causal process. Because in our potential outcomes framework, remember, suppose we have a time machine, we talked about causality in terms of counterfactuals. And with our DAGs, we have an implied counterfactual. Banana peel causes slipping. The implied counterfactual there is no banana peel, no slipping. Remember, a causal effect is a comparison between two states of the world. So when we're looking at a DAG, and we'll see one on the next slide, the very simplified one, we can think of a comparison between those two states of the world. The state of the world where you are exposed to the treatment, in this case a banana peel, and the state of the world where you're not. Banana peel causes slipping. Or the indirect effect. So maybe banana peel causes slipping by making you imbalanced. In the parlance of social science, this indirect effect is what's called a mediating variable. And what mediating means here is intermediate. There's an intermediate effect between the banana peel, your imbalance, and your slipping. We're still capturing a causal effect that originates at the banana peel. But whether or not there is a mediating effect, whether or not there is an intermediate outcome, depends on what you want to look at as a social scientist, as a leader. Questions so far? Riri, was that a question or a stretch? All right. So we're building out these assumptions that make DAGs a good graphical representation of our causal model. Causality moving in one direction, a DAG is acyclic. Causal effects happening only in two ways, the direct effect and the indirect effect. And completeness. And what we mean by completeness is a DAG is meant to describe every causal relationship in that system. So in our very simple example up there, banana peel causes imbalance, causes slipping. The only thing that causes you to slip is imbalance from a banana peel. There is nothing else in this system that can cause slipping. There is nothing else in this system that can cause imbalance. In this very simple example, the only thing that can make you imbalanced is a banana peel. This is a very strong but very simplifying assumption. Basically, we're saying we know everything about this model, which of course in most situations, most instances, we don't. The commitment to completeness means that we can also describe, like I was saying a few slides ago, the lack of a causal pathway. So who here has slipped recently? On the ice? There is no causal pathway in this DAG between ice and slipping. What we have done is describe a complete causal model by assuming out some variables. That might not be good practice. It's our job to interrogate the assumptions of this causal model. The lack of an arrow between, say, ice and slipping implies that there is no causal effect there. Assumed in our directed acyclic graph is a complete causal model. Questions so far? So let's start out with a really simple DAG. We've got our causal model that we were working with before, we've got banana peel causing slipping, but what else is in there? Actually, what else is in this DAG that wasn't in one before? Okay, so what do you think that means? Yeah, great job. So I said drinking, but taking our pictogram and turning it into a DAG, we've got banana peels cause slipping, but we have one other variable at play now. We've got drinking. And what drinking might cause you to do is, one, slip in and of itself, but two, hit more banana peels. In this DAG, we have three random variables. We've got the outcome variable, slipping. We've got the treatment variable, banana peel. But we have this new variable, D, drinking. There's a direct path from banana peel to slipping. It's represented by an arrow, so we know that there's a direct causal effect there. But there's this second path, this backdoor path, drinking, which causes both slipping, but also causes you to hit more banana peels. Importantly, this backdoor path is not what we would refer to as a causal effect. Though it is causal, what it describes is a process that creates spurious correlations. We talked about spurious correlations a little bit when we read the causality chapter in Bergstrom West. But the idea is, if we have data on banana peels and slipping, the fact that some people are out there drinking is going to change fluctuations in our data. And fluctuations in our data are what determine correlations. More broadly, the idea of a backdoor path is one of the most important things we can learn from our DAGs. What we're going to see in regressions at the end of this chapter, or at the end of this lecture, I should say, is the notion of omitted variable bias. And a backdoor path in a DAG is very similar to our notion of omitted variable bias, in that it represents a variable that might determine the outcome, but also impacts the treatment, in this case, banana peels. If we were regressing this in a statistical model, not controlling for whether or not people are drinking, in terms of the DAG, leaves open the backdoor path. In terms of the regression, presents us with bias. Remember, bias in the statistical sense means something that changes the way you're getting your data. In this case, not controlling for whether or not people are drinking creates omitted variable bias. With regards to this specific DAG, drinking, which influences both whether or not you slip and also how many banana peels you hit, is called a confounder, because it's a common cause of both these variables. It's called a confounder because it confounds our ability to discern the effect of banana peels on slipping in a naive comparison. Now, this is very, esoteric in some sense, but it should also resonate with all of you. Remember, when we say data, all we mean is information. And all we mean when we say we need to close backdoor paths is we need more information about the causal model. We can broadly think of a backdoor path as follows. Sometimes B, whether or not you hit a banana peel, takes on different values. And sometimes S, whether or not you slip, takes on different values. This is true both because hitting a banana peel causes you to slip, so whether or not you hit a banana peel will cause slipping to take on different values. But it's also because drinking causes slipping to take on different values. And that bit of correlation between banana peel and slipping is now purely spurious because of the existence of this backdoor path, because of the existence of drinking. I threw a lot at you right there. Any questions so far? So that's really fine and good, because what we're doing is trying to get more information and trying to make decisions with that information. Maybe I shouldn't drink because I might slip on a banana peel. But what happens if we don't know whether or not people have been drinking? What do you guys think? If we don't know whether or not people have been drinking, and that's the same DAG there, but now the drinking variable is unobserved. In the case of a DAG, we'll represent this with dashed lines to show that it's not an observed effect. Now the causal pathways are the same. Banana peel causes you to slip. Drinking causes both more slipping and more banana peels. But because we haven't observed whether or not you're drinking, we can't close that backdoor path. And that's why this is a confounding variable. Like I said at the beginning of this lecture, DAGs are really, really powerful, really, really helpful in thinking out causal models. We want to think about all the potential effects there and what happens with these causes and effects as we move forward in time. I say this not only to help explain what we're doing, but also as a side point, as you guys are writing your final papers, maybe you want to include a DAG. Certainly not required, but it might help you think through the data-driven decisions that you're making. So let's try and build out a DAG together. And suppose we're interested in the effect that a college education has on future earnings, on how much money you guys are making when you leave Sweetbriar. To answer that question, we might want to draw a DAG. We might want to consider the full causal model. Because unlike experiments where we can randomly assign treatment to college, or treatment to whatever, in college, we don't really randomly assign things. You guys all chose to come here, hopefully based on what your available options were, and this being the best possible decision. A college education is not random, like treatment and experiment. It's chosen based on your preferences and your constraints. So if we wanted to know how much a college education increased earnings, what are some variables that we might want to put in our DAG? What do you guys think? Yeah, Juliet. Okay. How many years you attend college, right? So maybe 1 year of college is different than 4 years of college. Excellent point. Elizabeth. Okay. Your major. Excellent point. What are some other variables we might want to attend? Yeah. Chloe. Which college, you know, whether it's highly ranked, whether it has a robust network. Ray Ray. Okay. That's related to degree program, right? Whether or not you're in honors. You guys are all thinking about stuff within the college system. Are there any variables outside of college that might influence your earnings? I saw, yeah, Cami? Maybe cost of living. Cost of living? Riley, you had a hand earlier. I didn't hear you, I'm sorry. Okay, GPA. Cost of living, GPA, major. Chloe, what else? Okay, so work experience, what else? I guess what kind of field that you're looking to go into, Elizabeth? State of the economy, excellent point, and really good job talking about things that might not be related to the college experience. Cost of living in the neighborhood was the same thing. What else? Debt? Yeah, Riley. Potential for growth? Great job, guys. The point that I'm trying to drive home here is when we draw our DAG, remember, we want it to be complete. We want to explore all possible causes and effects here. We also want to simplify. So here's the DAG that I drew. We've got the treatment variable D. Typically, D refers to a treatment variable. It was a little confusing on the last slide when we had it mean drinking. But here we've got the treatment variable, your education. Included in education might be many of the variables we were talking about. How long you stay in the program, what program you're in, whether or not you're an honors student, what your GPA is. We can sort of subsume this all into some ill-defined variable called education. We've got the outcome variable. We want to know if college increases your earnings. We should figure out what your earnings are. But we've got some other factors that we might think influence both the decision to go to college and your earnings. So we've got your parents' education, students whose parents went to college are more likely to go to college themselves. We'll talk about that in a second. We've got family income. This might be related to state of the economy, like someone said. It might be related to something else someone said. How much money your family has is probably going to determine both whether or not you're going to college, but also how much you're making later in life unrelated to that. And then we've got this all-encompassing variable that I just called other stuff, other background factors. And I said B for background. Questions so far? So I know we're all very new to this, but who wants to take a stab at interpreting this DAG? And let me give you a hint. When we interpret DAGs, usually we want to start at the bottom and move our way out towards the outcome variable. Yeah, Chloe. Right, your background is going to influence both whether or not you get an education and also whether or not your parents got an education. Importantly, we notice that background factors are unobserved in this model. We drew them with dashed lines. So one background factor might be your mother's innate educational ability. We're never going to be able to observe that, but certainly it's going to dictate whether or not your mother went to college, and it might dictate whether or not you go to college. Okay, so Chloe got us started. We've got this unobserved variable or set of variables, other background factors. It influences both whether or not your parents went to college and whether or not you're going to college. What else? What can we learn from this DAG? Yeah, Sita. All right. How much money your family has influences how much money you're making. What else? What else can we learn from this DAG? Anyone have anything they want to add to that? Chloe. Your parents' education influences whether or not you go to college. It influences family income. Family income also influences whether or not you go to college. Excellent point. And finally, whether or not you go to college and how long you go to college for and your college major and all those other variables that we included in this influence earnings. Questions so far? Put differently, what we're doing with a DAG when we're making this graphical representation of a causal model is we're telling a story. Here's the story that I think this DAG is telling. We know that college education is not random. It's chosen given your subjective preferences and your resource constraints. But in this DAG, there's no connection between background factors and earnings. No direct connection, I should say, which is an assumption. And you're free to call foul on this assumption, right? If you think that background factors impact both schooling and a child's own productivity, then you might think there should be an error there. But the story that I think this DAG is telling is that background causes both your optimal level of education and your parents' optimal level of education. There's also the direct effect of your parents' education on what you get. And we can come up with a bunch of different convincing reasons for this direct effect. Maybe because they went to college, they expect it of you. Maybe because they went to college, they serve as a model for you. Maybe there's some other causal effect, like they didn't go to college and you want to do something different. Then we have this backdoor effect that higher parental education seems to correlate with higher family income, which is going to impact both whether or not you can pay for school, but also impact future earnings. Questions so far? And remember, this is just our assumption of the model. We assume that we have a complete list of factors, but certainly we might not. What do we do once we have this DAG drawn out and we've told this story? I find it useful to list all direct and indirect causal paths. So who wants to tell me what the causal paths are? Peyton, can you name a causal path? All right. Background to parents' education, to college education, to earnings. Remember, when we're talking about the causal facts, we want to know between treatment, your education, and outcome, how much money you're making. So great job. We can start with background, and we can go from background to parents' education, to college education, to your earnings. Chloe, is that a hand or a stretch?
Sort of, but I think I might say
All right.
just that the parents' education directly impacts family income as well as directly impacting what education you get and then what your earnings will be.
All right. So we had the causal path from background to parent to you getting income. We also have the path from parent to income to you getting an education. What else? We've got, by my count, 4 causal paths. We've got the causal effect of education on earnings, the direct effect, education to earnings. And then we've got 3 backdoor paths. We've got income, which influences both whether or not you're getting an education and your future earnings. Thank you, Chloe. We've got parents' education, which influences whether or not you're getting an education and also income and also earnings. And then we've got background factors, the backdoor path number 3, which influences whether or not you're getting an education, but also influences parents' education, which influences income, which influences future earnings. What we've done here is create a systematic way of exploring the causal paths. The problem, as we saw earlier, is that background factors are unobserved. So we have this open backdoor path that's going to create a systematic and independent correlation between whether or not you get an education and how much money you're earning in the future. Put differently, open backdoor paths introduce bias when comparing educated and uneducated workers. Questions so far? So suppose we want to explore the impact of class size on test scores. Again, we want to assume a graphical model, draw a DAG, and we want to think really carefully about what goes into that DAG. So if we want to know the causal effect of class size on test scores, what might go into that DAG? Shekinah, what might go into that DAG? I can't hear you, I'm sorry. What might go into the DAG if we want to explore the causal model of class size on test scores? What? Okay. Studying. Great job. What else might go into that DAG? Yeah, Chloe, then Riley.
Well, the example of the actual size of the class and all the scores.
Right, we want the treatment variable, class size, and we want the outcome variable, test scores. Great job. So we've got whether or not you studied, how big your class is, and what your test score is. What else? Lily. Okay, GPA coming into the class. What else? Yeah, Ray. Okay, attendance or participation. Great job. Anyone have anything else they want to add? Yeah, Annika. Okay, type of exam. Great job. What else? Emily D.
Whether or not they do in class reviews.
Okay, whether or not you reviewed. Is that Kaya? Teacher quality, great job. Remember, when we're writing this DAG, we want to come up with everything that can go into our causal model. So certainly, Chloe, you're right. We need our treatment variable, class size, and we need our outcome variable, test score. But maybe we want ability, and someone said GPA. GPA might loosely measure ability. It might not. We want motivation, so whether or not you're motivated to study, great job. Maybe we want some variables that you might not typically think of as influencing test score, but certainly do. Like, again, household income. For arguably worse, it seems like students with higher socioeconomic statuses are performing higher on tests. We want to model that in our cause. And I have et cetera. Remember, we can just throw a bunch of things into a catch-all term, an other factors variable. So we might think all these things go into the DAG, all these things go into the causal model, but the DAG I drew, just to keep class simple today, and certainly we can add complexity, is just class size influences test score, and other stuff influences both of them. Other stuff here is a confounding variable because it influences both test score and how big your class size is. How might other stuff influence how big your class size is? Well, wealthier students tend to have resources that let them go to smaller schools. Someone said honors students, certainly an other stuff variable, might be in smaller classes because they're honors. That can go with ability. Motivation might influence whether or not you're in a smaller class. So someone said attendance. We might think attendance and motivation are very similar, right? So maybe it's not class size explicitly, but experienced class size. The 2 points here are, one, we can represent other stuff with just a catch-all term. And 2, we need to think very carefully about how this other stuff is influencing. But there's an important question embedded in that, which is once we've drawn this DAG, once we've thought of what the causal model might be, can we explore this causal relationship statistically? And remember, this is not a stats class. What we're doing here is thinking about it conceptually. So to explore these causal relationships statistically, we want to do something that's known as regressing. To regress in a statistical model, we formulate a data-generating process. It's a very circular definition. Data-generating process is the process by which the data are generated. But we already did that. We drew a DAG. A data-generating process is a graphical, or a DAG is a graphical representation of the data-generating process. Why do we want to know about the data-generating process? Because when we are making decisions in a data-driven world, we think there is something orderly and predictable about the way the data come to us. We believe that test scores, for instance, are generated by a predictable process. So what we've done is we've thought about how the data come to us. We've drawn it out in a DAG. Now we want to write it out mathematically. And again, this is not a math class. So we can gloss over a lot of the math here and just think about the idea. All we're doing with this math is formalizing an idea, which is test score is some function of a bunch of stuff, including class size. And you'll note importantly that this stuff is additive. Maybe that's not the right way to think about this model. Maybe class size is interactive with other stuff. But in this model, what we've done is assume that test score is a function of a bunch of stuff. One particular of that stuff is class size. And when we estimate a causal effect, what we want to know is the impact of that particular factor, in this case class size, on our outcome. Put differently, when we are ruling out alternative explanations, we want to estimate beta. And in particular, we're estimating beta sub CS, beta CS, beta class size. Questions so far? So let's talk about this beta coefficient. So we've written out this model, test scores equal beta naught plus beta class size plus other stuff. If we want to generalize this to other causal problems more generally, we have beta naught, which is an intercept, beta 1, which is the slope. So we've got this hypothetical data generating process. I just made this up, but test scores is a function of some intercept, some baseline test score, minus 0.5 times class size, plus 5 times ability, minus 5 times how lazy you are. To change this data generating process into that general form that we have above, we've got the intercept, the slope, and we've got these nuisance terms back here, other stuff. So our data generating process looks a lot like our simple regression model up there. Again, and importantly, in real life, we almost never know all the causal factors that go into a model, either because we don't know that they're a cause, or they're unobserved or unmeasurable. So earlier, when we were talking about what might influence test scores, we talked about a bunch of things which might rightfully go in the model: attendance, GPA, how good the teacher is. That didn't make it into this model. So one of the things we can do is critique a model based on how the data generating process was written out. Questions so far? But assuming this is the true data generating process, let's think about John Gregory Brown. Because he's in a class with 20 people in it, he's got a natural ability of 2, but he's pretty lazy. He's got a laziness factor of 4. So if this is the true data generating process for John Gregory Brown's test score, what does he get on the test? All we have to do is plug and chug, so let's solve it together. We start with 100, that's the intercept, that's the baseline test score. And we subtract 0.5 times the class size. So what's the class size? So what's 0.5 times 20? 10. So 100 minus 10, that's 90. Plus 5 times the ability, what's his ability? His ability is 2, so 5 times 2, also 10. So we're back to 100. Minus 5 times how lazy he is. How lazy is JGB? 4. So 5 times 4 is 20. JGB's test score is 80. Everyone get 80? What if the class size changes? What if the class size increases to 21 students? Now what's JGB's test score? And importantly, none of that other stuff has changed. So all we have to do is change 0.5 times that class size. So what's his test score now? It should change by 0.5, right? Because the class went from 20 to 21 students. Nothing else has changed. 0.5 is that coefficient, minus 0.5 is the coefficient on class size. So now his test score should be 79.5 instead of 80. Everyone see why that's the case? Any questions so far? So let's take this data generating process that we hypothesized and apply it to some naturally occurring data. Let's look at the average test score across California school districts, and let's look at how they match up against student-teacher ratio, which is our measure of class size. What do you guys think? What's this scatter plot telling you all? Does it look like test scores are going up or down with class size? Not by that much. It's hard to tell. It's a really noisy measure. We've got some big classes that are scoring pretty well on tests. We've got some small classes that are scoring pretty poorly on tests. There's a lot of stuff going on. But this statistical technique that we were talking about, regression, in particular OLS, ordinary least squares, is a statistical method which gives us the function that minimizes the squared distance from the points to the regression line. Again, very verbose. This is not a math class. You don't need to know what that means. But what it means is, what it means mathematically, but what it means conceptually is that in performing this statistical technique, we're given a line of best fit. And that line of best fit gives us an intercept term, beta naught. So it looks like the average test score, the baseline test score, I should say, is 698.9. That's before we take any measure of class size into account. And as student-teacher ratio increases, average test score goes down by about 2.28. So what are we learning from this statistical technique? That school districts that have higher student-teacher ratio have, on average, lower test scores. This regression, this statistical technique, is telling us that there is a negative relationship between test score and class size. All else being equal. In order for this effect to be causal, we need to assume ceteris paribus, which is Latin for all else being equal. Only when all these other relevant factors we talked about, how motivated you are, how good the teacher is, how lazy you are, what your GPA was, how much you studied, what your attendance is, only when all these other factors are on average equal to 0 do we get a good causal estimate, and good in heavy quotes there. All these other factors are captured in this nuisance term, this error term. For our regression, all else being equal means that for any value of class size, we have, on average, the same value of this other stuff. So what do you guys think about that assumption? Do school districts with unusually high student-to-teacher ratios also have equally good teachers? Do school districts with unusually low student-to-teacher ratios have just as many poor students? Do students with average student-to-teacher ratios also have average student motivation? What do you guys think? Yeah.
There's probably a lot of differences there, so it's very difficult to say everything else.
Right, there's a lot of differences there. It's probably difficult to say all else being equal. What we know from our regression is that on average, students in districts with an average class size of 15 have on average higher test scores than students in districts with an average class size of 25. But from our causal model, we can think of two reasons why this is happening. One, the direct effect of this lower student-to-teacher ratio, or our other effect of everything else that's going on in the world. And in order for the effect of student-teacher ratio to be causal, in order for it to be identified, in order for us to have ruled out alternative explanations, everything else, which we capture in this U term, needs to be on average equal regardless of school size. Questions so far? So just to sum up what we learned today, in any data set, this linear regression, this OLS, gives us the line that best fits the data. And we think, as people making decisions in a data-driven world, that there is some data-generating process that generates what we're observing. It's helpful to think about what this data-generating process looks like. And I really mean looks in the graphical sense of a DAG. To come up with a causal interpretation, we want to know how the change in one factor affects the change in the outcome. But in order for this to be interpreted as causal, we need unobserved factors, that U, that nuisance term, to be independent of X. And by independent of X, this is our identifying assumption. Remember, we're talking about identification strategies here. Our identifying assumption is that on average, everything in all other stuff, everything in U, on average is equal whether or not we know anything about your student-to-teacher ratio, or whatever our treatment variable is. If knowing something about the treatment variable, whether it's student-to-teacher ratio, whether it's you went to college, whether it's you slipped on a banana peel, if knowing something about that treatment variable changes what you know about other stuff, then it's not going to be a good causal estimate. Questions so far? So I know this is really difficult because we're talking about these mathy terms, these statistical terms, but we're talking about them in a very conceptual way, somewhat informal way. But this is exactly how I want you guys thinking about it moving forward. Because as we noted when we were talking about our various book chapters, we don't always have time to dive into the data to make sure that people are reporting standard errors correctly or anything like that. But we can always think generally and think broadly about what some of these unobserved factors are and whether or not they're independent of the treatment. Questions? All right, so we'll be back here on Friday morning. Don't forget to exit through the side doors. We're discussing, I forget which book chapter, but it's on your syllabus. Have a good one, everyone.